Hey guys, so I'm going to walk through what I understand of this heat equation nonsense, and it will either help you or it'll confuse you more and you can help me, but I think I get it. As far as the three things we need to talk about, we need to demonstrate that the equation makes sense physically, and also that the units make sense, and then also that it mathematically works out. I think it makes the most sense to start with the physical, because that is the one that actually makes the most sense to me. The idea is that the change of heat, so change in heat, needs to be equal to both any heat that's coming into the area and any heat that's being generated in the area. And the analogy that came to me first was just thinking of a chunk of farmland or something. You can either bring food into your, your home or your acre of ground, or you can grow it there. But those are your only two options. Stuff can come in from outside, or it can be grown there. That's why the change in heat is equal to the stuff that flows in, plus the stuff that's generated in the space that you've already got. And then from a conceptual standpoint, if what you're interested in is the rate of change, you're just dividing each of these things by time. So that's why conceptually it makes sense in a physical sense. As far as the units go, you have to look at all of the different constants and equations and things that are given to us. And if you look at that page with the U, the heat capacity, the rho, the mass density, and all that stuff, the equation that we're trying to make sense of, this thermal energy density equation expression, just requires you to go through and replace all of the different units. So the actual equation, I didn't copy it here. Oh, here it is. This looking thing, all of those different pieces just need to be replaced with whatever the units are. So the thermal density times the volume is going to be the amount of heat energy that's actually in a place. This E equation that she gave us is the thermal energy density. That's this part. And then you just multiply that by the volume, which in the picture that she drew and I didn't copy is this little chunk of cylinder that's got the area for the circle, and then the thickness of it would be delta x. That's where this piece is coming from. So this expression, E of xt and A delta x, is going to be replaced with these other units, the heat capacity, the density, and the temperature. So that's all I did on the other side of the equal sign here. I just wrote those out. And then as far as how the units for that work out, the heat capacity is in calories per gram degrees Celsius. The density is in grams per cubic centimeter. The time derivative of the temperature would be degrees Celsius per second or per time or something. And then this area times delta x is going to be the volume, which is cubic centimeters. And on the left, we have the time derivative of the thermal energy density, which is going to be calories per cubic centimeter per second or something. And then that's being multiplied by the volume, which is in cubic centimeters. So it's really just a question of, do these units check out? And on the left, the volumes are canceling. On the right, grams are canceling, degrees Celsius are canceling, and cubic centimeters are canceling. So that you have calories per second, which is what we're supposed to have for the equation. I think that she made a mistake on this slide where it says the derivation of the heat equation. I think this stuff is not supposed to be on the left. I'm not sure, but if you include that there, it throws the units off. You can look at that again, maybe I'm wrong, but I think that this E of xt is equal to the heat capacity times the density times the temperature. So when you take the derivative of it, you get this stuff with a partial derivative of the heat, the temperature. But if you include these things over here, I think it throws the units off. So I have not emailed her or called to check on that, but I'm thinking that's wrong because this equation I don't think works out with units. Oh, here's the equation that I was going to write down so that we were looking at calories per cubic centimeter. This was cubic centimeter. The heat capacity was calories per gram degree Celsius. Density, gram, cubic centimeter. And this would be the degree Celsius per time again if you took the derivative, and that's cubic centimeter. So without the stuff in front of that E, these units make sense. But if you throw in what she had, the heat capacity and the density on the left side, then it would throw off the units. That's why I'm thinking that's wrong. It might have just been a copy error. But moving on to a math sense, this is where we're just trying to actually take the derivative and make sure that it works out or that we're allowed to do it. So we look at the three parts of the equation. The change in heat, that needs to be equal to the energy flowing into the space plus the heat that's actually generated in there. And the three expressions that she's got in the slides represent these three different quantities. The one that we just looked at were these units. I haven't looked at all the rest of the units to make sure that they work out. I was just looking at that first expression, but it would be a similar process. The heat energy flowing across boundaries is essentially the area of the boundary times the change in heat in area. That's what this phi is. It's the change in heat divided by the area, and so if you multiply it by the area, you're getting the change in heat. And this expression is saying the change in heat at one end minus the change in heat, or the heat at one end of the hockey puck versus the other, because this is the area and this was x, and this was x plus delta x or something. I didn't copy that part of the picture, but all we're trying to say is that there's some heat amount here, there's some heat amount there. You take the difference, and that tells you how much is in this hockey puck space. Then the heat generated inside is this Q thing times the volume. Q is the heat generated in a spot, and if you multiply that by the volume, you're going to get how much energy is in that hockey puck, or how much heat was generated in there. So the actual math just requires you to put the equation on the left, the rate of change of heat in time, and then these other two quantities on the right. And then when you divide by the volume, that's how you're getting from this step to that one. That means the A and the delta X are disappearing from this. The A's disappear from that. A delta X disappears from that. And this stuff in the middle needs to be over delta X. That's where this expression comes from. And that's why at this point you take the limit, because we're no longer looking for the change in heat in the entire hockey puck. We're just looking at one little spot. The slice needs to be infinitely thin so that we can actually come up with legitimate calculations. So the only place where the delta X shows up after we've divided by the volume is here in this middle term. And so when you take the limit as delta X goes to 0, that's what the partial derivative is. So that's why this expression becomes the partial derivative of phi, or whatever that Greek symbol is, with respect to x. And then these other things stay here because we've already divided out the volume. Once you get to that expression, we have essentially the heat equation, but we need to replace this phi. There was an equation for it. Did I not copy it down? I might not have copied and posted it. Give me a sec. I have the slide up elsewhere. So, yeah, she has it written down as phi of xt is negative k naught x partial derivative of u of xt with respect to x. So essentially what this stuff is here, she's just replacing this with that, because this was also one of the equations. Just talking about what is the the heat flow in that particular spot. So the more interesting thing, though, is this chunk without heat sources, because we're saying that if Q is 0, meaning this part will go away, and the heat capacity, the density, and this K are constants, meaning this, and this are not going to change, then we're allowed to manipulate this equation a little bit more. This drops out, you can divide both sides by this, and that's where you get this constant thing in front of the other stuff. If you call that kappa, you get the expression as we're looking at it in class. A partial derivative of u equals some constant times the second derivative of u. And that's all I have for you. That's my understanding of it so far. Hope that helps.